Welcome to This Explainer. Today, we're putting on our detective hats to investigate one of the most persistent, head-scratching mysteries in all of modern physics. I am absolutely thrilled to guide you through this because we're diving into some truly groundbreaking cosmological papers by Riccardo C. Storti. If you've ever felt like the universe is playing a massive trick on us, well, you're gonna love this. So let's just jump right into the investigation. For years now, astrophysicists have been sounding the alarm about a full-blown crisis. They've been telling us that our fundamental understanding of the universe, the standard model of cosmology itself, might actually be broken. But what if we've just been looking at it all wrong? What if the universe is working perfectly, and this whole apparent crisis is actually just an incredible, mind-bending trick of perspective?
Act 1. The Broken Universe.
Okay, so to understand the trick, we first need to understand the problem. In the world of cosmology right now, there is a massive 5 sigma discrepancy. And in statistics, 5 sigma basically means it is virtually impossible to be a fluke. This has scientists literally panicking about the expansion rate of the universe. On one side, we have measurements from the early universe. Using the Planck satellite to look at the cosmic microwave background radiation, the CMBR, scientists calculated an expansion rate of 67.4 kilometers per second per megaparsec. But then, on the other side, when we look at the late universe, our local cosmic neighborhood, using the cosmic distance ladder, that rate suddenly jumps to 73. That is a glaring difference. We're talking about 2 gold standard measurement methods giving us 2 completely different answers. But here is where Storti's research entirely flips the script. It turns out this whole tension, it's an illusion. Think about it. We're trying to measure the pure global expansion of the universe, right? But we're doing it from inside a galaxy. We are standing deep inside a massive local gravitational field that actively distorts our vantage point. We have essentially been trying to measure the speed of a flowing river while caught inside a localized whirlpool.
Act 2. The culprit. Location bias.
So the universe itself isn't broken at all. Rather, the specific places we've historically chosen to measure from carry a massive hidden bias that throws our math entirely out of whack. Historically, because of pure technological limits, astronomers had to just use the brightest objects they could find to measure vast distances, things like standard candles, supernovae. But where do those bright objects live? They sit way out in the chaotic, dynamically unrelaxed peripheries of galaxies. They're out in the wild outer limits, constantly getting pulled and pushed by incoming matter and local gravity. Now contrast that with the viralized cores, the stable, relaxed gravitational centers of those galaxies. These cores represent a much, much truer cosmic reference frame. This brings us to something really fascinating, the concept of a space-time drain. According to Storti's framework, galaxies act exactly like this. Not only is space-time expanding outward cosmologically across the whole universe, but locally, space-time is also flowing inward toward the center of mass of the galaxy. So if you're measuring something sitting on the chaotic outer edge of a galaxy, you're getting hit with a dual stretching effect. And this extra local stretch is exactly what artificially elevates our local measurements to that problematic number of 73. It's not new physics, guys. It is just local gravity playing tricks on our light. So the obvious question is, if the outskirts give us the wrong number, what happens if we look at the stable centers? Act 3. The smoking gun manga data. To prove this location bias isn't just some neat idea on a chalkboard, we need data. We need unprecedented, highly detailed data. Enter this staggering number right here, 10,096. That is the number of galaxies analyzed in the SDSS-DR17 manga dataset that's used in this framework. We are not talking about a handful of local observations here. We're talking about over 10,000 independent galaxies, which gives this resolution undeniable, crushing statistical weight. And this dataset, it's an absolute game changer in astrophysics. Before this, telescopes pretty much used a single fiber optic cable, which essentially gave us one blurry single dot of light to represent a whole galaxy. But manga uses hexagonal integral field units to capture complete 3D data cubes. It maps the movement, the rotation, the chemistry across the entire two-dimensional face of a galaxy. It is quite literally like tree ring dating for the cosmos, letting researchers finally cleanly separate those chaotic outer edges from the stable, viralized cores. So, the absolutely crucial moment is, what happens when Storti's parameter-free equation is actually applied to the stable cores of those 10,096 galaxies? The result is an astronomical Hubble constant of 66.95 plus or minus 1.44 kilometers per second per megaparsec. I just want you to take a moment to appreciate how beautiful this is. When we simply stop looking at the chaotic outer edges and instead analyze the stable cores of over 10,000 galaxies, the infamous Hubble tension completely disappears. Poof, gone. The local measurements and the cosmic background measurements suddenly converge to within less than 1% of each other. The standard model of cosmology is totally safe. We just needed to clean up our local biases. But the wildest part is, this framework doesn't even stop there. Because by figuring out the true flow of spacetime within a galaxy, Storti inadvertently solves a completely different companion mystery.
Act 4. Redefining the edge.
It sounds like such a simple question, right? Where does a galaxy actually end? You'd think astrophysicists would have this locked down by now. But defining the physical edge of a dark matter halo has been incredibly messy. So we're shifting gears here for a second, from kinematics to the actual thermodynamics of a galaxy's edge.
Currently, there's this thing called the extrapolation ambiguity that's causing massive headaches in astrophysics. Because we can't clearly see the edge of a galaxy's dark matter halo, scientists essentially have to guess where it ends using these totally arbitrary mathematical cutoffs and made-up density profiles. This is exactly why estimates for the mass of our own Milky Way vary so wildly, from 200 billion all the way up to a staggering 1.5 trillion solar masses. We've basically just been guessing where to draw the boundary line.
To fix this, Storti defines the true geometric edge dynamically. He defines the virial radius as the splashback, or turnaround surface. Now, this is the exact physical boundary, the exact tipping point, where matter falling into the galaxy reaches its maximum expansion right before the outward pull of the universe's expansion takes over. No arbitrary guesses, no made-up density profiles. It is a strict, undeniable, dynamical boundary. And that brings us to this incredibly specific magic number right here, 2.7255 Kelvin. This is the exact ambient temperature of the cosmic microwave background radiation. It's the baseline temperature of the universe itself. And in this new framework, it serves as our ultimate visual and thermodynamic milestone. So how do we actually find this edge without guessing? It's done using something called the phenomenological geometric temperature ansatz. I know, it sounds like a mouthful, but here's how elegant it is. First, you calculate the effective temperature of the local space-time expansion. That's the manifold temperature. Next, you just move outward from the galaxy center until that local temperature drops to match the cosmic background's exact baseline of 2.7255 Kelvin. The exact spot where those temperatures perfectly match, boom, that is your boundary. You have now established the true virial radius and the exact mass of the galaxy, completely deterministically. Now, theory and math are fantastic, but what about hard physical proof? Is there an actual object out there in space that perfectly embodies all of this?
Act 5. The Standard Lighthouse.
Yes, there absolutely is. Out of the 10,000 galaxies analyzed, there is one unique singular galaxy that serves as the ultimate cosmic anchor. Its official catalog name is Manga 1457004, but we can just call it the Standard Lighthouse. This single galaxy is the definitive smoking gun for sure. When you look at the Standard Lighthouse, both its stellar mass and its dynamical mass perfectly and independently converge exactly to the cosmic microwave background Hubble constant. It has zero peculiar velocity relative to the cosmic frame, meaning it is sitting perfectly, beautifully still relative to the expansion of the universe. It physically proves out there in the real world that local astronomical measurements absolutely do converge with global cosmological ones when you strip away that location bias. I want to read this powerful quote directly from the paper because it just hits the nail on the head. The crisis was never cosmological, it was epistemological, born of our technological compulsion to observe the brightest objects which happen to reside in the most biased environments. We really thought the universe was broken, but it was just our own technological limitations blinding us to its true elegance. The universe wasn't giving us the wrong answers, we were just measuring from the wrong spot. So by simply shifting our perspective from the chaotic outer edges to the calm, stable centers of galaxies, a terrifying 5 sigma cosmic crisis entirely vanishes. The standard model is safe. It really makes you wonder, doesn't it? As we look out into the vastness of space, are there other cosmic crises out there merely waiting for us to just shift our perspective? Thanks so much for joining me on this explainer. Keep questioning everything, and I'll catch you next time.